Good morning, everyone. Today we're going to continue our discussion on the lesson on multiple linear regression in the context of financial data. So this discussion is quite different from your FinArts course. This is all about still about multiple linear regression, but we will not really dive deep. We will we will have the we will discuss the main important points of multiple linear regression in preparation for the future subject or the future lesson on machine learning, because it's important for us to understand or to know regression, because we're still going to use that for machine learning. Okay, so we talked about I will not belabor this point, class. Now, one important concept in finance, which is the CAPM, capital asset pricing model, actually makes use of multiple linear regression. You might not have seen it that way, but you learned about CAPM, I'm sure, in your previous subjects, and you have a formula for that. And that formula actually is a simple linear regression, okay? Unless you're dealing with multi-factor models, which is multiple linear regression. Okay, so last time, what we did was to briefly explain what multiple linear regression is, or simple or linear regression is, what it is. And we said that the equation in general is that y sub I is equal to a certain constant plus beta 1 times x sub I, which is your independent variable, plus your residuals. So I gave this class to you, and then we defined what these variables are. I'm sure this is not the first time you're meeting this or encountering this lesson. You've had several subjects, also DSI subjects, okay? DSI LITIC, and I don't know what those other subjects are, but you were exposed to linear regression. We said that there are assumptions as far as linear regression is concerned. Linearity, your y and x should be linear in relationship. It doesn't make any sense to do linear regression if you're, let me first leave it first. If you plot your y, your dependent variable, and your x independent variable, and if they behave this way, okay, so there's no sense in creating a linear model between the two, because this seems to be a quadratic model. Okay, so that's what we're saying here, linearity. If the relationship between y and x is not linear, or it could be polynomial, say the plot shows this way, then it doesn't make sense to do a linear regression model out of that. Okay, so that's the first condition, linearity. And then we also said that the errors, we defined what errors are last time. We said that errors are results of the results. It's a difference between your actual value and your predicted value. Okay, your actual value is y sub I. Your predicted value is denoted by y hat sub I, which is equal to, okay, last time you said that this is actually equal to, that's y sub I. This is your beta null plus x sub 1, and then for beta 1, then x sub 1. Assuming this is this is your this is a simple linear regression. Actual minus predicted. So that's your residual. The residuals play a very important role in assessing whether your linear regression model is valid or not. We mentioned the term blue last time. Blue. So those of you who were not in our session last time, please review the video. That's because I discussed this in greater detail. Best linear unbiased estimator. Okay, the goal is to create this model where you define your parameters, beta null and beta 1. I'm talking of a simple linear regression model here, class, and that these parameters, class, are the best linear unbiased estimators. Okay, and this will happen only if we are able to uh, uh, if we fulfill the assumptions of classical linear regression model. So one is that the errors are not correlated with each other. Okay, so every observation, let's say y1, y2, y3, these are your actual values, y4, etc., will generate their own residual. E1, epsilon 1, epsilon 2, epsilon 3, epsilon 4, etc. Okay, and how is this obtained? By subtracting it to your predicted value, y hat sub I. So this is y hat sub I1, y hat sub I2. Again, class, y hat refers to your predicted value. So your actual value minus your predicted value is equal to your residual. Now, we're told here that the residuals are not correlated. Okay, so E1 should not be correlated with E2, neither should it be correlated with E3, etc. Now, there's a distinction between, so let me discuss this now. It's very important. So it really depends on the nature of your data, because the data can be what we call cross-sectional, or it can be cross-sectional time series, okay? And the last, it can be panel data. So what's the difference between these three? So you can take a look at it in terms of the units or the individuals and the time period. Okay, time period. For cross-sectional data, we are looking at many units. And then time period or time frame, only one. Okay, so an example. Let's suppose we're taking a look at the, let's say, GDP of many countries. Let's say, let's just focus on ASEAN 5. So we have, that's too small. Let's say all the countries of the world. Okay, so there are 180 plus countries. So from, say, what could be the first one? I'm not sure. Azerbaijan up to Zimbabwe. So those are all the countries that you're looking at. And then the time frame, so you're looking at GDP only in, let's say, 2024. So we have one time period, okay? And your units or your individuals are many. So this is from 1 up to whatever the number of countries, let's say 180. So from Azerbaijan up to Zimbabwe. Several countries, GDP only for 2024. Okay. All right. This is called a cross-sectional data. Many units, one time period. Now, in this case, your residuals, okay, the independence of residuals will not be so much of a concern. Okay. Why is that so? Because the units, class, do not have any logical arrangement. You can reorder this. You can put the Philippines first. You can reorder it by, let's say, region. So, ASEAN muna. Okay, then North Asia, then South Asia, and then America, etc., etc., etc. So if you order it that way, then the order of your residuals will change. So your epsilon 1, epsilon 2, epsilon 3 will be different if you arrange it alphabetically, or you arrange it from letter Z to letter A, or you arrange it randomly. Okay, the arrangement of your residuals will vary. In other words, class, the units do not have any a logical arrangement. So in that case, in a cross-sectional data, the independence of errors are not so much of a concern. Okay. Now compare that with a time series. For a time series, class, you only have one unit, and the time period is many. Example, let's just take a look at Philippines. Only one unit, right? We are looking at GDP of the Philippines, say from 19, so the units is only one, okay? But the time period is many. So let's say the measure of GDP, okay, from 1970, 1971, etc., up to 2024. Okay, and this is all Philippines. This type of data is called a time series data. And here, okay, the independence of errors is an important factor. Okay, because you'll generate residuals here. Epsilon sub 1, error sub 2, error sub 3, error sub 4. And the errors, okay, cannot be jumbled, cannot be reorganized. Why? Because there is a logical arrangement of your data. You cannot start with 2023 and then jump to 2010 or 2010, and then jump to 1988. That cannot be done because the data is arranged according to a logical arrangement by time. Okay. So in this case, your residual 1 will have to be followed by residual 2. It will have to be followed by residual 3, etc. And this is where the relationship between errors are important. So are they correlated? Is error 1 correlated with error 2 or with error 3, etc.? Okay, so this quality here, this assumption here of independence of errors is only valid for time series or panel data. Okay, because panel data is you have many units and many time periods. So it's like having this example, you have 180 countries, let's say from Azerbaijan up to Zimbabwe in, let's say, year 2010. And then that is repeated, Azerbaijan to Zimbabwe 2011. Okay, and then again, the 180 countries in 2012, 2013, 2014. So for a panel data becomes a bigger data, and this panel data affords us with a more robust data, okay, as compared to a cross-sectional data or time series data. Okay, and so this independence of errors is relevant for a time series data or a panel data. Okay, let me pause for a while if the discussion of cross-sectional data, time series data, and panel data is clear. Kindly chat, please, in the chat box. I hope you can respond faster, class. Okay, thank you. And I hope there will be more people responding. Okay. All right. Thank you so much. Okay, let's clear the drawings. Okay, so we also discussed homoscedasticity. In the interest of time, class, I will have to request you to watch the video we had last Wednesday. Okay, I also discussed these concepts, okay, so that we can go to the main one. All right. So how is the regression line determined? If you have, let's say, your variable y and your variable x, and then you create your scatter plot. This is the plot of your y and x. Okay. The question is, what is the regression line? Or what is the line of best fit? What will best what what best defines the relationship between y and x? So is it this line? Or is it this line? Or is it this line? If you take a look at this, we can come up with infinite number of solutions. When I say solution, that's associating or coming up with the function, okay, of y on x. So we're relating y with x. But the question is, what is this function? And if you recall, you can create a linear function where y is equal to mx plus b. Okay? Or in our equation a while ago, y is equal to beta null plus beta 1 times x. This is what you learned in your elementary algebra, which is just the same as this one. Beta null is the intercept, which is this one. Beta 1 is your your slope. Okay, so we would like to develop this one by determining what are the beta 1, what are the parameters class. That's what you mean by developing the association or coming up with a relationship between y and x, being able to determine the parameters. But you can come up with several beta null and beta 1. Okay, so the question is, what is it? Can there be more than one? Okay, more than one, we call it ordinary least squares. Or we also call it the line of best fit. Can there be more than one line of best fit? Or can there be lines of best fit? The answer is no, class. There can only be one. Sorry, na-erase ko yung ano. There can only be one line of best fit. Sorry. This is only one class, only one. And how do you determine that line of best fit class? So this is your actual data. This is your line of best fit. We said a while ago that it's only one. This line of best fit has this quality, this attribute. Okay, so if you compare this line of best fit, okay, this is class. This is what you call your. This is your y hat. Okay. That height is your y hat. Well, this height, class, this is your y sub I. This is your actual y, this point, right? This is your actual y. This is your y hat. This is your predicted value. So the difference between them is your epsilon, that's your residual. Okay, so each point here, you'll have your residual. This one, it will also have your, it's the residual. So those points that are on the line, the residuals are all equal to 0. And so last time, class, just quick review, we said that if we sum up all the residuals, summation of all our residuals from I is equal to 1 up to n being the number of observations that we have. Okay, the answer will always be equal to, I discussed this last time, it will also always be equal to 0. So the regression line will generate a line where the residuals, the sum of the residuals is equal to 0. Why is that so? Because the regression line will have points that are above the regression line and points, the actual points that are below the regression line. And if we add all of them, class, it will be 0. So we don't use this. What we rather use is the squared of the residuals. Because for this one, for example, this is your y hat, right? The point on the line is your y hat. This point is your actual y. So y sub I minus y hat, this is your epsilon, and it's your positive epsilon. On the other hand, those points that are below the regression line, they are negative epsilons. Why negative? Because it's always the actual y sub I minus the predicted. The predicted here is this one, and it's above your y sub I, right? So that will be a negative. So if you get the squares of that, okay, then it will not generate a sum equal to 0. Okay, there will always be a value to that because the negative residuals will be squared, will become positive, and we are able to add up all now these squared residuals. So if you take a look at this class, the line of best fit is the line that minimizes this one. Okay, it minimizes the sum of your error squared or your residuals squared, which is equal to the actual minus the predicted. The difference between them, this is your epsilon, right? Squared. Okay, which is equal to your actual minus this is your predicted value. So it's now expressed as beta null plus beta 1 times x1. Okay, this is your y hat. Okay, so you do some calculus with this. Okay, and then you'll be able to determine and solve what beta null and beta 1. And this beta null and beta 1, okay, are the parameters that will give us the line of best fit, okay, or the OLS class. It's called OLS, ordinary least. The least here means least, L-E-A-S-T, least. The smallest class, the smallest what? Squares, okay, squares of the residuals. All right, so I hope that's clear, class. I'm just discussing again those which I think are very important. So I hope this discussion clarifies, class, yung the concept behind ordinary least squares. So quickly now, class, make sure that your packages are loaded: quant mode, performance analytics, and ggplot. We have been exposed to this before, so no problem. So I guess that our first topic, which was returns, risks and returns, univariate, single, and also multivariate portfolio. I hope that the use of quant mode and performance analytics has really prepared us for deeper discussions in the future. So here we're getting SPY. SPY class is an exchange traded fund. This is representative of Standard and Poor's, which can be used as a proxy for the market. In the Philippines, we use PSEI, Philippine Stock Exchange Index. That's very important, class, for CAPM. Okay, because in CAPM, if you recall, class, it's used for valuation, and you'd like to predict the returns, the excess returns. Okay, if you recall, class, what's the formula for CAPM? Anyone, please? Capital asset pricing model. Anyone? Capital asset pricing model. Hello, class. Okay, yes, thank you, Jason. Okay, what's RA, Jason? What's RA? That's your return of your asset, right? So we're taking a look at the return of your asset, and it's equal to your risk-free rate, okay, plus what? You have your beta there, and then multiplied that by what? Return of the market minus return of the risk-free rate. Okay. So how do you determine the return of the asset? It's equal to risk-free rate plus your beta times your return of the market minus your risk-free rate. Okay. Okay, if you take a look at this class, this is a linear model. This is your intercept. This is your slope. And you have your excess returns that's based on the return of the market. So we have to know plus the return of the market, okay, and get the excess returns of the market over its risk-free rate. So this reduces into a simple linear regression class. So that's what we're doing now, class. We're preparing ourselves to do the CAPM, okay, apply CAPM using R, using regression. Okay, so we'll go through this. Okay, thank you, Jason, okay, for sharing that CAPM formula, class. So this is what we have in mind, class. Okay, and this is just, it's exactly equal to class y sub I is equal to beta null plus beta 1 times x sub I plus your epsilon. Or if I remove the epsilon, I have to put a hat here. Y hat is equal to beta null plus beta 1 times x sub I, because this is your predicted value without the epsilon. Okay, I hope I'm not going too fast. Please watch the video class, no, for a deeper discussion and a slower discussion. Okay, you know this class. Here we can download SPY, which is your Standard and Poor's, a proxy for Standard and Poor's. And Standard and Poor's, by the way, Standard and Poor's 500 is your proxy for the market. Okay, so we need this, and also the stock that we're looking at is Apple. And then you know the syntax here, class. Source is equal to Yahoo, from to is equal to, given the dates. And then this one is actually not needed anymore, but we're just putting it anyway, because this is the default true, which means that R will create these two objects. So kindly run this class if you haven't done so. I will not run it anymore because I have run it in the past, last Wednesday. I think I have here SPY and here SPY and Apple. Okay, kindly confirm, class, if you have the objects already, please chat. You'll need to download it anyway because the exercises will be based on the SPY and Apple. Thank you. How about the others, please? Feedback from the others, please. Okay, thank you. Thank you, Jason. Thank you, Kind Botkin. Nalilito ko lagi. Sorry, Kind na. Only 2 plus? Let's give your classmates a few more seconds. Please confirm, please, so that I know when to continue, because I feel that it's an exercise in futility if only 2 students have the data. You are 15. It's only 2. How about the rest? Okay, thank you, Natalie. So still waiting for the 12 other students. And good. Thank you. Okay, thank you. Okay, so let's continue, class. So we have these two assets. Remember, class, that the objective is for us to, again, let's just begin with the end in mind. No? We want to create a CAPM model out of this. We want to determine the returns of Apple, okay, given your risk-free rate, RFR, plus your beta times the risk, the return, sorry, not your risk-free rate, plus the return. Well, it's a risk-free rate, return of the market minus return of your risk-free rate. Okay, so as I said, class, we would want to determine the returns for Apple. This is valuation. And one of the basic tools of valuation is CAPM. Okay, so we are applying, this is an applicatory lesson, class. Okay, this one we'll have to take. We'll have to get that from Fred. Okay, because we can't get this from Yahoo. But this one, class, Apple, this one, market, the market is SPY. Okay, and the RA is Apple. Right? So we'll have to determine what is your beta. Okay, but we will first do this, okay? And we will not use RFR first. We will use just a regular, we will determine that using another beta null, using our LM. Okay, so moving forward now, here, okay, this was discussed last time, but let me just, this one I requested the class to write. So I'll give you a few moments. Let's create SPY returns. Okay, and remember this is from performance analytics. Return that calculate. Okay, and return that calculate will generate an NA first row. Okay, so we have to, we're using NA.omit. And then what returns are we asking R to compute? From the SPY data set, okay, then we want the SPY that adjusted, and we want the continuous returns, log returns. Okay, so this is pretty straightforward. I'm sure you understand this already because we have been exposed to this in the past lessons. So we're building up on what we have been learning. Okay, so when you take a look at this, I'm sure, hopefully, if you have been very faithful then to reviewing your lessons and being committed to learning our lessons, class, I'm sure you'll understand this already. So here, on the other hand, we're computing for Apple returns. Again, NA.omit. This time we're using calculate returns, which is also from performance analytics, which is the same class. So we're just using two different functions which give us the same answer, just to be exposed to other functions. Calculate returns. Notice it's capital C, capital R. Return that calculates long, small c. Last time we also used daily returns, small d, capital R, but that's coming from QuantMove. And the difference between return that calculate and daily returns is that daily returns will generate a 0 returns in the first row. This one will generate an NA, and that's more realistic and correct, theoretically correct, because there's no prior value. Okay, I'll give you a few seconds, class, please. Once you're done, kindly please chat in the chat box if you have computed for SPY returns and Apple returns. Okay, I hope you can respond for faster, class, so that we're just reviewing the past lessons, class. We're just reviewing the past. I hope we can move further than just the last one. So I really need your cooperation and need you to respond faster, class. And thank you, Jason. Okay, thank you, Natalie. Good. Yan. Okay. I'm happy with the progression, with the added pace. John, thank you. Mildred, Justin pala, not John, sorry. Sorry, Justin. Okay, more replies, please. About the others, only five students out of 15. About the others, you need a little bit more time. Thank you, Laila. Okay, Vic, thank you. At least we reach more than half. Konti pa. I'll give you time to. I know that's quite long. My goal is to go beyond what we discussed last Wednesday so that there will be improvement kasi kung hanggang din tayo sa lesson last Wednesday, parang wala rin tayong dadagdag. A few more seconds, class, please. I guess I have to really say and give credit to those who are participating. So anyway, pag na-record ko ito, makikita ko class yung yung those who are answering, those who are responding, and those who remain silent. Kasi pag nagre-remain silent kayo, class, imposible naman, class, na ginagawa nyo, tapos natapos nyo, tapos hindi man lang kayo magre-respond. Mas sobra yon, no? Last 10 seconds. Okay, so we can see, class, that if we check SPY returns and Apple returns, where's my SPY returns? SPY returns, this one. These are log returns, by the way. So notice that there's no NA here at the start. So these are log returns, and I also have the same for Apple returns. Okay, then, okay, where's that? Okay, so what do we do here, class? We create another object. We create combined returns, then we merge Apple returns and SPY returns, and all is equal to false, right? Before, all is equal to false means only include those rows that are common to both. If one row is not existing in the other one, remove that. Although that's a very, this is the last option that you should do before removing any rows that are not available in any of them. There are ways in order to address that instead of removing first. So I'd like to inform you that this should be the last priority. Okay, last priority to class yung all is equal to false. As I said, there are better ways of imputation. If, for example, let's say December 20, 2024 returns for Apple is missing, okay, then what we can do is just impute it by following the returns on 2023. That's called your last object carried forward, last observation carried forward, LOCF. But anyway, that's another topic. So we have now these combined returns and then change their column names. Okay, kasi Apple adjusted pa rin yun. But let's change it into Apple returns and SPY returns. And then check if there are missing values. And then if there are missing values, then omit. Okay, again, class, this is the, in this case, the omitting here should be the last thing that we should do. Okay, because we can do imputation. Okay, all right, I'll not run this because I have already run that. So you'll now have a data, an object combined returns where you have Apple returns and SPY returns. Okay, kindly confirm again, please, if you have that object. I just want to know if you're able to follow. You now have combined returns also. Okay, good. Thank you. Thank you. Thank you so much, class. Okay, although 1, 2, 3, 4 pa lang. Sige, let's give your classmates a few more seconds. Okay, good. Thank you. All right. Great. Okay, thank you, class. Thank you. Okay, so let's move forward. Okay. Now this one I shared with you in the file that I posted. This is it's there. So this is just ggplot, one of the most powerful data visualization tool. The package is ggplot2. Okay, the function is ggplot. Okay, take note that we're using combined returns. So you first define the data to be used. However, combined returns class is an XTS object, and an XTS object will not work with ggplot. So we have to convert it into a has.data.frame. We're not really changing the combined returns data, which is an XS object. We're only changing it here as far as this function is concerned. Okay, and then we define the mapping. This is called your mapping. This is your data class. So this is the syntax of ggplot. In the previous video, I discussed with you about creating layers. That's what ggplot2 does. Layer upon layer upon layer. That's why you have the plus here. Plus, and then plus, and then plus, and then plus, and then plus. You're building several layers. Okay, this one is that layer for, let me just put this here. Okay, this is the layer for the, okay, for the mapping of the y and the x axis. We're saying here aesthetics, short AES, that what will be plotted on the x-axis is SPY returns. What will be plotted on the y-axis will be the Apple returns. Okay. By the way, class, in CAPM, when you plot the returns, the market will always be on the x-axis. And by the way, what you plot are not the prices. I've seen students make the mistake of plotting the prices. You don't plot the prices, you plot the returns. Okay, the returns, the market returns on the x-axis, the asset returns on the y-axis. And then again, plus. Do not put the plus at the beginning of the code, at the beginning of the line of code. Okay, that will generate an error term. And then the shape here, we're saying point. So this is for your scatter plot. Okay? And alpha has something to do with jittering. I'll not discuss that now. Color is equal to dark blue. And then give it plus a title, scatter plot, Apple versus SPY, plus x-axis label, y-axis label, and then theme minimal. There are different types of themes. So when you run this class, you'll now have a scatter plot for Apple returns and SPY returns. There you go. Okay, you can see that there's a strong positive correlation between your Apple returns and your SPY returns. we would want that your dependent variable y to be highly correlated with your independent variable x. As you can see, there's a strong linear relationship between the two, and a linear regression model would fit this relationship well. Okay, all right. Then let's now create the model. Going back to the previous one, we said that the objective is to create y sub I is equal to beta null plus beta 1 x sub I. Beta 1 x sub 1. Beta 1 x sub I. Okay. So the function class is this one. So first we have to convert our combined returns. Let's create this data. Sorry, this object regression underscore data underscore. I think I created so long a name. You should have shortened it, but that's okay. Anyway, because I used it already in the other parts here, so I'll not be changing it anymore. Unless you want it to change it class, use another one. Just make sure that what you're using there is the same as regression data df. Okay, so the linear model class is used this way. So for some of you were not my students in FinArts, so you'll be meeting this for the first time, or you were not here last Wednesday. LM stands for linear model. And how do we use linear model? We define the dependent variable Apple returns, and then here you have your tilde. Tilde button. Yeah, I think this is your tilde, and then your spy that returns. Okay, this is your independent variable. If you have several independent variables, then just plus whatever the independent variables you have, plus x2 plus x3, etc. And then you define the data. The data is regression df, data df, which is a data frame already. You cannot use the XS object class. Okay, so let's run this class. Kindly run this class, LM model. Okay. So if you run this class, okay, okay, I'll run this. LM model class. You'll have this. Or na-run ka ba yung summary? Wait, class. Bakit din yung generate? Okay, so not yet, no? So if you run this LM model, who among you was able to generate this LM model? You can see that in the environment LM model. Kindly please chat if you were able to generate the LM model, which is a list. Okay, good. Okay, good. All right, so if we click this class LM model, it contains many information, many outputs. Okay, for one, it contains the coefficients. If you click this, so you'll have the intercept and the spy returns, their values. Okay, you can also find here your residuals. Remember, the residuals are the differences between your differences between your actual value and your predicted value. Okay, so last time I illustrated to the class. I won't illustrate that anymore, class. Please watch the video because I illustrated to the class how this was generated, how this was obtained, and that's very important. So it's very important that you watch the other video. For lack of time, class, I won't discuss that anymore. Now, you can generate the results, class, using summary. But here, let's create this. Let's create an object lm mod underscore summary. Let's call it lm model. Okay. So we have here LM model summary. This is related to your LM model class. And then summary of LM model. So let's run this. And then you were able to create an LM summary model, which is also a list class. Okay. And then let's run here summary of LM model. Let's just run that. And then you can find this output. Okay, once again, chat, please, class. If you got the LM, the summary of the LM model. Okay, good, thank you. All right. Let's wait for the others. Okay, good. Okay, thank you. Thank you, class, for responding. Okay, I do hope the others are able to follow me. And please, those who were not there last Wednesday, please watch the video. I'm skipping some of the discussions there. Okay. Now take a look at this result. The call portion class tells us the function that you used. So we were using the LM function. The formula is Apple returns associated with SPY returns. Data is equal to regression data DF. And then here we have some 6-number summary about the residuals. We say that this is very important. In fact, before we can really say that the model is reliable or best linear unbiased estimator is to have a residual diagnostics. Check the residuals again for heteroscedasticity, for correlation among residuals, etc. Now take a look at the output. So we have here the intercept. Okay, the value is 0.003552, etc. You have here the standard error of the estimate. This is your SEE, standard error of the estimate. This is your T value and the P value. SPY returns also here. Okay, what's important for us is to take a look at whether your estimate, your parameters, is statistically significant or not. Remember, class, this is your beta null, this is your intercept here. I mean here, class. This is your beta null, this is your beta 1. The question is beta 1, is this 1.189? Okay. Is it possible that this is just coincidence? Okay. So was there just, this is a random coincidence that this is 1.18? So that's the question. That can be answered here, class, by the p-value. And the p-value tells us if your variable, the value of your variable is statistically significant or not. Okay, how do we do that? We compare it with our alpha. alpha is your level of significance, which is by default 0.05. Of course, we can use another alpha. It depends on the field. Okay, in the medical practices, they may require a lower alpha. Okay, maybe 0.01 because they're testing the efficacy of let's say drugs, of medicines. In our field class, 0.05 is the usual practice. So we compare now the p-value here. This 2e to the negative 16 class means, okay, it means you write 2 here. It's 2 plus. And then you move 16 places to the left because it's negative. Negative 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that means points here, 0. So you'll have 15 zeros and then 2. So that's 0.000, 15 zeros and then 2. So that's practically equal to 0. So we say that the p-value is equal to practically 0 and it's less than 0.05. Okay, our level of significance alpha. And the rule is, before the rule class, this one is, it's not a descriptive statistics class, but rather it's an inferential stat. So if you recall from your basic stat, for inferential statistics, we have a null, a hypothesis. We're hypothesizing something. And the null hypothesis is that your beta 1 is equal to 0. Okay, but I should not be discussing this anymore class. Sorry, I'm tempted to be more detailed. Okay, so let me just dispense with this. And then just the conclusion. The conclusion here, class, is that we reject this hypothesis, x2 plus. Why? Because the p-value is 0. And the level of significance is 0.05. And I said in the previous video that when the p-value is low, the null must go. When I say low, it means less than 0.05. When the p is low, the null must go. And what's the null? Beta 1 is equal to 0. So what's our inference? This must go plus. We reject the null hypothesis. So there's strong statistical reason to believe that your estimate for SPY returns is a value other than 0. In fact, the average is 1.89. Okay. Right, I think I discussed too much already with this one. Again, class, my request for you is to watch the video. This is 3 stars, which means I keep on going back to that class to again discuss what has been discussed in the previous video. Okay. So this one, I gave this code also to you. If you run this, you'll have this. This superimposes the regression line class. That one. That's the regression line. And you notice that, so you have here geom point. This is the same one as the previous one. And then geom smooth. Method is equal to LM. So if it generates a line, this one, okay, where is this line coming from, class? From the LM model. So we know that the slope of this one, class, we know that the slope of this one, okay, the slope is 1.18 ba? 1.19 approximately. And okay, so what does that mean, class? Rise over the run, no? So for every 1 unit increase in your X, there's a corresponding 1.19 unit increase in your Y. Okay, so if we apply that to our model, this is our model. How do we interpret this? for every 1 unit, okay, 1 unit, 1 point increase in SPY returns, there's a corresponding 1.18 unit increase in your what class? The answer is Apple returns. Okay. For every 1 unit increase in SPY returns, then there's a corresponding 1.18 unit increase in your Apple returns. So you can see that Apple returns is very sensitive to any changes in SPY returns. And the reverse is true plus. For every 1 unit decrease in SPY returns, there's a corresponding 1.19 units decrease in your Apple returns. Okay, so let's this one class, this just explains what we went through. So this is for your reading class. Okay, also this one, null hypothesis, etc. Okay, so let's take a look at the confidence level now, class. So the values here, class, ito, yung SPY returns at saka intercept. These are what we call point estimates. But in reality, class, the real value of SPY returns and the real value of intercept really lies between it should be a range between these two values. Okay, between what values? So we can the confidence interval is equal to the estimated coefficient. The estimated coefficient are this one, class. Okay, itong 0.033 and then 1.19. Plus or minus the critical value times your standard error. You actually have your standard error here. Okay, it's a matter of determining your critical value. I leave this an assignment for you, class. How do I show the confidence interval? But technically, class, ito lang yun, no? Okay, let's show this, class. So I didn't give this to you, class. I think confidence interval, I think I gave it there, but if not, kindly write it. So let's first get the coefficients. We know the coefficients are the intercept and the SPY returns. Okay, we can directly get it from LM model. Okay, and then let's get the confidence interval of our LM model. So if you run this, class, you'll have this. You'll have this. So your intercept is negative 0.0355. And then it's okay, confidence interval niya, class. So what does this mean, class? If you take a look at your intercept, right? So 95% confidence interval. So this is 95% in the middle, which means this is 2.5 to 2.5, right? So this is 2.5%. And this is, class, this is also 2.5%. Or take a look at it cumulatively. This is, up to this point, is 97.5%. Because that's 2.5, 95, the total is 97.5%. And confidence in class tells us that your intercept is between negative 0.318 and positive 0.001, etc. While SPY returns is between 1.14 and 1.24. Now you notice the intercept, class, it touches 0. From negative to positive, which means that 0 is a possible value here. That's why internship, class, is not significant. Okay, if your confidence interval, class, will touch the 0 value, then it's not significant, because it tells us that there's a possibility that the real value for the intercept is 0. On the other hand, SPY returns, it will not touch the 0 point plus. It's between 1.39, 1.113, and 1.24. So 0 will not be touched here, these two intervals. Okay, so that makes it statistically significant. So we are rejecting that the beta for SPY returns is equal to 0, because it's not possible for the beta for SPY returns to become 0, because it will not touch the 0 at the 95% confidence level. Okay, so I said here, if the coefficient does not include 0, it is statistically significant in that confidence level. Okay, let me pause again for a while. Okay, we have some more minutes. Are you able to follow, class? Kindly confirm, class. Maybe you have questions, or if you're able to follow, please confirm by responding in the chat box, please. Thank you. Thank you. Okay, good. So, question lang, class. I'm sure you learned this concept before in your stat, but is this the first time you're looking at this in the perspective in the using our tools, class? First time ba? You're taking a look at this through R, no? Okay, good. Thank you. Yeah, and I hope you're finding it very useful, class. Because those questions that before, when you have the power to compute it, when you have the power to understand what's happening and compute it in R, it really makes sense. It really allows you to have a firmer understanding of those lessons. Okay, so we'll just discuss the goodness of fit next time, class. But suffice it to say, let me just go back to our regression. Goodness of fit here, class. Here. Okay. So here we have the residual standard error. Okay, what is this, class? This is actually your, as for maybe you have met this before. This is also your standard error of your regression. Okay. This is your, it's like the standard deviation of your residuals. Okay, so it's telling us on the average, there's a 0.01217 difference between your actual Apple returns and then the from your Apple returns predicted. Remember, you're using SPY returns in order to predict Apple returns. Okay, and the residual standard error, or standard error of the residuals, it's just like the standard deviation of your Apple returns. So remember, your standard deviation measures the degree of distance, average distance between your actual X value, okay, and the mean of the X. All right. Then we have here multiple R squared, 62%, 62.8, and the adjusted R squared, 62.7%. So this tells us of the proportion of the percentage of the variation class or variability of your target variable or your dependent variable, which is Apple returns, Apple ret. Okay, that can be explained by your dependent variable or by your model. Our model is SPY returns class. Yeah? So it means it's able to explain 63% approximately of the variation of your Apple returns. Okay, which is quite high. You're talking only of one predictor. So what about the other 27%? Then it can be explained by other variables. So we're just looking at one predictor here, SPY returns. So that's your This is the goodness of fit test. It's called goodness of fit test because you are also you also have a inference test here, class. And it's equal to beta 1 is equal to beta 2 is equal to beta 3 is equal to beta dot 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 is equal to beta sub n is equal to 0. So what do we mean by this? Goodness of fit test. So we're, especially this is true for multiple linear regression. You have several predictors. So we're testing if all of them, okay, all of them class, joint test, all of them are all equal to 0. Okay, but since we only have one variable, beta 1, because this is just a simple regression, so the hypothesis here becomes beta 1 is equal to 0. And it's similar now to the individual t-test here. Because here we're testing beta 1 is equal to 0, diba? Here we're also testing beta 1 is equal to beta 2, etc. But we only have one. So it's equal to beta 1 is equal to 0 also. That's why take a look at the p-value. It's the same. Okay, because it's the same test actually. Only that here, class, here we're using t-test. Okay, here we're using t-test, and here we're using f-test. Note. Yeah, anyway, sige, yung note na yan, I'll just discuss that later. Okay, so go back again. It's almost time. Our time flies so fast. Okay, here, class. I just want to discuss this, no? At least makaabot tayo dito, class, yung sa R squared, no? Yung 62% yung adjusted R squared. How was that generated, class? So quickly, let's see. I have a few more minutes. Okay. I just want to define here, class, 3 metrics. You have your SSR, SST, okay, and your SSE. So the formula is that your sum of the squares of your regression is equal to the sum of your, what's this, class? This is your actual value minus your predicted value. So this is your residuals, no? Others call this the SSE, sum of the squares of your residuals. Okay, so sum of the squares of your residuals is your residuals, class. Great. On the other hand, we have this one, sum of the squares of your total is equal to your actual minus the average. Actual minus the average. So let me just quickly, okay, let's just quickly solve, class, this one. Very quickly lang, class, and then I'll end here. For those of you who need to go, please just leave na lang, no? Okay, so we need to compute this SSR. I'll call it SSR, class, alt minus. And it's equal to the sum. Okay, sum of what? Why sub I, class? Everything can be, class, obtained from your LM model. Okay, if you take a look at our LM model, class. So what are these? Intercept, okay. These are your residuals, class. But, and what are these effects, class? Can somebody tell me what are these effects? This one, class, what's this? If you take a look at this one, combined returns, 0.009769, okay, 9769, okay. So hindi siya effects, di ba? It's not this one. So where can we get the actual value here? We need the y sub I, class. Do we have the y sub I here? Anyone, class? You have the predicted value here, y sub I, fitted values. So where do we get the y sub I, class? Anyone, please? Okay, for lack of time, class. Well, we can get it from combined returns, class. If you recall, class, combined returns. What was we converted combined returns? What was that, class? Anong value yun? Okay. So what's y sub I, class? I'll just use combined returns. Combined returns, class, dollar. That's your Apple returns, right? So this is your y sub I. And then minus your predicted value. That's from your LM model, dollar. So your predicted values are your fitted values there. Okay. Sum of what, class? Sum of the squares. So we square this first and then get the sum. Okay. So is this correct, class? Is this formula correct? So let's print also SSR. So the question is this correct? What do we do first, class? So this one minus this one. We square it first, class, right? Okay. And then we sum. Okay. So be very careful, class. There's a world of difference between summing the combined returns minus the LM. Sum it up. Remember, if you sum it up, it's equal to 0. And then if you square that, that's equal to 0. As compared to getting the difference first, squaring it, and then summing that up. So you see, it's different. Okay, it's different. And then last one, class, this one. Okay, before we go again, just for recording this class, SST, sum of the squares total, alt minus. So that's equal to sum again, sum. Okay, open parenthesis first. So your y sub I is the same as this one. And then minus. This one is different, class. It's just the average. Okay, I'll just copy that. Control V, and then it's just the mean. Okay, and then you square that first. Okay, 1. So mean of this. Okay, 1, 1, 2, 3, 1. Kulang pa ba? Wala. Okay, So SSR. Okay, 0.37. Okay, 0.37, which is what cannot be explained because this is the residuals. What can be explained is 0.63. Okay, so thank you so much. We'll just continue with this next meeting. I'll repeat that process because it was already too fast.